देख लो यहाँ पर, ठीक है। Electrostatic formula is basically, so first one is charge per unit length formula. Charge per unit length. So suppose we have a conductor whose length is given as L, and the charge distribution on this particular conductor is Q. So if I want to find the charge per unit length, that is denoted by letter lambda. So lambda is nothing but charge over length, that is Q over L. Unit is coulomb per meter. Coulomb per meter. As far as dimension is concerned, charge is basically I is equal to Q over T. So Q is equal to IT, I into T. That is AT or IT. Both dimensions are possible per unit length. So it is ATL inverse. ATL inverse. So dimension of lambda is ATL inverse. Second formula is basically charge per unit surface area. So as far as, suppose we have a metallic plate that is given whose length is L, breadth is B, and if I want to find the surface charge density, that is given by letter sigma. So it is charge per unit area. So sigma is equal to charge upon area. Unit of charge is coulomb, area is meter square. So the unit of sigma is coulomb per meter square. Coulomb per meter square. Next, formulas for Gauss theorem basically. First one is called as electric flux. Third formula is electric flux. So electric flux is defined as line integral. This is called as line integral E dot ds. E dot ds is equal to E ds cos theta. E ds cos theta. So basically this is the formula for line integral. Phi is nothing but Gauss theorem. Phi is equal to 1 by E naught times the total charge enclosed by the body. What is E naught? E naught is nothing but permittivity of free space. Permittivity of free space, of vacuum or free space. The value of E naught is 8.85 into 10 की power minus 12 coulomb square per Newton meter square. Coulomb square per Newton meter square. So if an object is placed in a dielectric medium, so we use the formula phi is equal to Q upon K E naught. Q upon K E naught. What is K? K is nothing but dielectric constant. So next formula is basically dielectric constant. So what is dielectric constant? It is nothing but a ratio of electric field, that is E naught. This is called as epsilon naught. Permittivity of any medium. Permittivity of medium to permittivity of free space, permittivity of vacuum. So K is nothing but E upon E naught. This is epsilon over epsilon naught, right? Next one is electric field formula. Electric field due to point charge. So electric field due to point charge. Suppose we have a point charge Q. We need to find the value of electric field at this point, which lies at a distance say R. So electric field is defined as force acting per unit test charge. E is equal to F by Q naught, which is nothing but 1 upon 4 pi E naught. Q into Q naught over R square divided by Q naught. Q naught gets cancelled out. So electric field formula is 1 upon 4 pi E naught Q over R square. Charge over distance square. So this is the formula for electric field or electric intensity due to point charge. Formula is 1 upon 4 pi E naught Q over R square. Next, formula number 6, that is electric field due to charge sphere. Electric field due to charge sphere. Now it is important to note that this article is quite important. Suppose we have a conductor. So we have a metallic conductor and we have a hollow conductor. So this is hollow spherical conductor whose radius is say R. Whose radius is R. We want to find the value of electric field at this point P, which lies at a distance of say small r from the center at this point P. So electric field at point P, that is electric field outside, the formula is 1 upon 4 pi E naught charge over distance square. That is electric field outside. Electric field at the surface, the formula is 1 upon 4 pi E naught charge over distance square. Electric field inside the electric field formula is 0. electric formula is 0. So inside basically electric field is 0. So if I want to plot a graph between electric field and distance, so field is plotted along y-axis, distance along x-axis, distance along x-axis. So we have a graph like this. So inside of electric field is 0. Outside we have inverse relation. So electric field inside is 0. Outside we have inverse square relation. So this nature of graph is called as basically ISG graph, inverse square graph. This graph is called as ISG graph. In case of solid sphere, all the formulas, in case of, this is hollow sphere basically. This is for hollow sphere, hollow sphere. In case of solid sphere, electric field outside the formula is same. Electric field at the surface, the formula is same. There is a difference of electric field inside the sphere, because in case of solid sphere, we have electric field inside. So electric field inside solid sphere. So electric field inside solid sphere. Solid sphere. So the formula is 1 upon 4 pi E naught. 1 upon 4 pi E naught. Q into small r by capital R cube. Q into small r over capital R cube. Outside formula is same. 1 upon 4 pi E naught Q over R ka square. Surface formula is same. 1 upon 4 pi E naught Q by R ka square. Inside we have a different formula, that is 1 upon 4 pi E naught Q into small r by capital R. And when we talk about the graph, so for graph, if I want to plot a graph between electric field along y-axis and distance along x-axis. So this is distance along x-axis. So inside electric field is directly proportional to radius. So we have a direct graph like this. So E is directly proportional to R. Outside we have inverse square relation like this. So we have outside inverse square relation. So the graph is ISG. Inside it is a straight line. In case of hollow sphere, see, electric field is 0. Electric field is 0. Hope concept is clear. Next important points. Next important result, that is electric field outside a spherical conductor. Outside a spherical conductor. So first one is cylinder. Electric field due to charge cylinder. Suppose we have a charge cylinder whose length is L, and the charge is Q on the surface. Suppose we want to find electric field at this particular point P, at this electric point P at a distance say R. So electric field at this point is nothing but E is equal to lambda upon 2 pi E naught R. This is the formula. In terms of lambda, E is equal to lambda upon 2 pi E naught R. In case of surface charge density, we have a formula sigma into R upon K times of E naught into small r. Sigma R upon K times of E naught into R. In case of when a charge cylinder is placed in free space or vacuum, so the formula will reduce like this. E is equal to lambda upon 2 pi E naught R. Lambda upon 2 pi E naught R. It is important to note that for solving numerical, we need to multiply the formula and divide the formula by 2. 2 cross 2, 2 by 2. So the formula will reduce to 1 upon 4 pi E naught 2 lambda by R. Why we are multiplying and dividing by 2? The reason is that because we know the value for 1 upon 4 pi E naught. The value for 1 upon 4 pi E naught is constant, and the value is 9 into 10 raised to the power 9 Newton meter square per coulomb square. This is the value for 1 upon 4 pi E naught. Inside charge cylinder, electric field is 0. Inside any conductor, if the conductor is hollow, right? Inside electric field is always 0. Next formula, that is electric field at a short distance from a charged conductor of any shape. So suppose we have a charged conductor of any shape and we want to find the electric field formula. So electric field at any point can be given by formula E is equal to sigma upon K times of E naught. Sigma upon K times of E naught. What is sigma? Sigma is basically charge over area. Sigma is charge over area. Charge per unit area. So if you place this conductor in a medium, So then we multiply by K. See, K times of E. Next, formula number 9. Electric field due to uniformly charged infinite plane sheet. So this is infinitely charged plane sheet. So if I want to find the value of electric field at this point P, which lies at a distance say R, at a distance say R. So the formula for electric field is E is equal to sigma by E is equal to sigma upon 2 times of E naught. E is equal to sigma by 2 times of E naught. This formula generally we use for single plane sheet. Suppose if in the exam they will give you a system of 2 plane sheets. So we have a system of 2 plane sheets. These are the system of 2 plane sheets. So on one sheet we have positive charge, second sheet we have negative charge. So let us assume we take 3 different points. So this point is P, this point is P, this point is Q, this point is R, this point is R, right? So as far as point P is concerned, the electric field formula is E is equal to E is equal to sigma upon 2 E naught. First, we'll try to find the value of electric field due to this positive charge, positive plate. So direction for positive plate is always away. Then same point, at point P, we need to find the value of electric field due to this negative plate. So formula for negative plate is same, but the direction is opposite. So E2, let us name this as E1. So this is E2 is equal to sigma upon 2 E naught, sigma upon 2 E naught. But the direction is towards negative plate, towards negative plate. So the net value of electric field will be difference of these two. That means they will get cancelled out. So outside the conductor, outside the plane system, electric field is always zero. Outside the system, electric field is zero. Similarly, at point R, electric field will be zero. At the mid portion, at point Q, the electric field will be addition of these two. So electric field will be E is equal to sigma by E naught. E is equal to sigma by E naught. I repeat once again. So in the exam, if they have given you a system of 2 plane sheets and they ask you to find the value of electric field outside the sheet, outside the plane system. So in that particular case, electric field is zero at point R and at point P. Inside we take the addition of these two. So it is sigma by 2 E naught plus sigma by 2 E naught. That is nothing but sigma by E naught. So inside we have sigma by E naught. This is formula number 9. Next one, work done formula. As we know, the formula for work done, V is equal to W by Q. So W is equal to V into Q. V into Q. What is V? V is basically potential difference. Potential between 2 points. That is VB and VA. Next, torque on a dipole. So we have tau is equal to P cross E. So when you remove cross sign, we have sine component. So formula is tau is equal to PE sine theta. When theta is equal to 90 degree, in that particular case, torque will be maximum, that is PE. Second case, when theta is equal to 0 degree, torque will be 0 in this particular case. Torque will be 0. Next important formula, that is of potential energy. That is work done by external torque on a dipole. So potential energy formula, we need to just integrate the torque from theta 1 to theta 2. So you need to learn the direct formula, that is PE cos theta naught minus cos theta. PE cos theta naught minus cos theta, right? So potential energy of electric dipole in external field. So formula is PE cos theta naught minus cos theta. This is important one. Please remember this. Next, capacity of condenser. As we already covered, capacity, that is charge holding capacity of an capacitor. So formula is C is equal to Q over V. Okay. So inside parallel plate capacitor, we have electric field formula. So it is nothing but Q over A K E naught. We know the potential difference formula between the plate of the capacitor, that is V is equal to E times of D. E is electric field, D is distance. Then capacity formula, that is C is equal to E naught A by D for a parallel plate capacitor. So we have 4 different cases in it. Suppose this is a parallel plate capacitor and we have air is filled between the plates. So when you have air as a dielectric, so the formula is E naught A by D. E naught A by D. So this is the formula for parallel plate capacitor. This is case number 1. Case number 1. Case number 2. Second case. When you have a dielectric in it, when you have a dielectric, say K. So the capacity formula will reduce to C is equal to K times of E naught A over D. E naught A over D. Third case. Third case. So when you have a metallic slab, whose thickness is T and distance is D. So the formula is C is equal to E naught A by D minus T plus T over K. C is equal to E naught A D minus T plus T over K. Fourth case, when you have a metallic slab. So when the metallic slab is inserted, when you insert a metallic slab. So in case of metallic slab, put the value of K as infinity. So 1 by infinity is 0. So formula will reduce to E naught A over D minus T. C is equal to E naught A over D minus T. So these are the four cases for a parallel plate capacitors. Clear? Next, energy stored in capacitor, that is formula number 17. So energy formula is half CV square, half QV, half Q square by C. It's easy. Next formula deals with series combination. So series combination of capacitor. In case of series combination, we connect opposite terminals together. For example, if we have a capacitor like this, so this is positive terminal and this is negative terminal. So you connect negative terminal of first capacitor to positive of second capacitor. So this is C1, this is C2. Opposite terminals are connected. So in case of series combination, charge is always constant. Potential difference varies. Potential difference varies, charge remains constant. So capacity formula is C is equal to 1 upon C1 plus 1 upon C2 up to 1 upon Cn. Clear? Last but not the least, that is parallel combination formula. Parallel combination. In parallel combination, we need to just add the charges. Why? Because charge are variable. Potential is constant. So in parallel combination, we have C1 plus C2 up to Cn. Clear? Yeah. So these are the combinations, parallel combination. So I've covered the entire chapter's formulas. So this is just for a quick revision.